And so I should mention to start with, it's based on a joint work with Ebrahimi-Fard. Nicolas Tapia and Lorenzo Zambotti. So we are exploring this idea of a non-commutative Wick calculus, and we have started with the first paper, but we intend to go on in that direction. So I will essentially explain the main ideas. I won't enter into formulas. There are many combinatorial formulas that one can derive from these approaches, and it's closely related to computations with lattices of partitions, and so there are many formulas, but I will insist more on the general algebraic picture than the combinatorial one. And I will start by recalling classical Wick calculus, because the idea is really to generalize to the non-commutative setting what happens classically. There are two classical uses of Wick calculus. One is in quantum field theory, and the other one is in probability. It's not very difficult to show that the two are extremely connected. I mean, one can move from one to the other by some translation rules using a suitable approach to QFT at least. So there's a common background for the two, but I won't insist too much on this. I will just explain on these two approaches or Wick calculus enters classically many constructions. I will start with the Wick work, so from 1950, with a simple toy model explaining what happens. So the idea is to say a toy model, quantum field theory, which you can find, for example, in the book, in the series of books by Zeidler. So I took this construction from his book. So look, for example, at the three-dimensional cube, and assume that you have periodicity conditions on the boundary. Then if you go to momentum spaces, they are, because of the periodicity condition, naturally quantized. So momenta look like Ni delta, say delta P, N1 delta P, N2 delta P, N3 delta P, with delta P 2P over L, and Ni integers. But it's convenient to make a sort of first renormalization, so Wilson type renormalization. And for reasons that will be clear later on, assume that these coefficients Ni are bounded by some integer n that can vary. So in this situation, one can make essentially all computations to understand how to construct free quantum fields out of this data. And so so without entering too much into details, what comes out is that there are naturally associated creation and annihilation operators indexed by the momenta. And they satisfy the usual commutation rules up to normalization. Yes. So we take this normalization, and so else. So if you have different momenta, everything commutes. So the point is that in that case, one can make all computations, and one can compute the energy operator associated to this system. So in that case, what you get is the sum of all momenta of AP dagger plus AP dagger AP over 2. And the problem, which was really the reason for the work of Wick, is that if you compute the vacuum energy what you get, because of the properties of annihilation and correction operator, what you get is something like the sum of P of I'm sorry, I missed the coefficient. Does the energy, associated energy, which appears where P is equal to the square root of a mass term plus P squared. So when you make the computation, what you find is the sum of a P of AP over 2. And of course, if you remove the Wilson renormalization and you let n goes to infinity, this is going to tend to infinity. So there would be an infinite vacuum energy. This is the principle for all this kind of arguments involving Wick normalization at the first step of construction of quantum fields, or also it also holds for solution of certain stochastic partial differential equations, for example. And so to remove this infinity, the solution that has been adopted, I think it was earlier to Wick, but this was really formalized by Wick, is to replace the operator product by the Wick product, or the normal order product, which is obtained simply by putting all correction operators at the left of annihilation operators. And if you do so, you remove the infinities, because when the annihilation operator is going to be applied to the vacuum, it's going to set it to 0, and so you have performed renormalization doing so. And so this is the basic reason why Wick products enter in quantum field theory. Now if we move to probability, Wick calculus looks at first sight a bit different, but in fact this is really the same ideas that are behind. In probability, the standard approach will be to start from square integrable functions of standard Gaussian variable. And construct Hilbert basis by so autonormalization out of monomials. If you do so, it's not. I mean, it's a standard exercise. What you get is the Hermite polynomials, which are also the say Wick powers or Wick monomials associated by definition to the standard Gaussian variable. So, there's again a notion of Wick product appearing here, and this can be generalized to all random variables, and this is the approach that I will use later on in the non-commutative setting. So if you start from a random variable with momenta at all orders, then you can define using exponential generating series Wick polynomials that are going to be different from the one in the case of a standard Gaussian variable associated to x in the following way. So you divide the exponential of tx by the expectation of the exponential generating series associated to the variable x. And it's convenient to write this identity that way. So you write this term as the exponential of the logarithm of the expectation of the exponential generating series. And what you get here is the exponential generating series for cumulants. So I insist on this because cumulants are going to play an important role later on. So, so this is classical Wick calculus. There are many things to say. It's a very nice theory, but I will essentially stop here on the classical theory and explain just one thing. It's convenient actually to axiomatize these various approaches, which all in a commutative setting essentially, because I didn't mention it, but the purpose of Wick's 1950 article was to relate Wick products, which are defined that way, so putting creation operators at the left of annihilation operators in products, to what is called time-ordered product, which is the products which are the products you obtain when you have a sequence of operators by putting ordering them by decreasing time ordering. And so the time-ordered product is commutative. The Wick normal-ordered product is also commutative, essentially by definition. And so the question Wick addressed was to find combinatorial formulas to move between the two. So it's a commutative framework. Here it's also commutative, and we're going to go for non-commutativity later on. But so as a first step, I will show to axiomatize this classical Wick construction. So the basic object in that case is going to be the algebra over real or complex numbers associated to a family of variables with the usual product and a coproduct. So which is the algebra map from H to H tensor H, which is obtained by declaring that the generators of the polynomial algebra have to be primitive. So if you do so, you get a Hopf algebra that is essentially an algebra equipped with a coproduct which is co-associative and is an algebra map from H to H tensor H. And what happens in this situation is that if you have a unital linear form on H, then you can induce from it a map, an endomorphism of H. So by convolution, this map is actually a linear automorphism of H, and so you can use it to transport the Hopf algebra structure of H to a new Hopf algebra structure. So if you do so, you obtain a new Hopf algebra structure. In particular, you obtain a new product. And what happens is that it's possible to account for the construction of Wick product using this strategy. So I will take only the example of random variables. The other one, I mean, the one of quantum fields is maybe even simpler. So, for example, if you have a sequence, say omega 1, omega n of random variables, then you can define a map lambda from H to the reals by declaring that lambda of xi1, xik should be the expectation of the product omega I1, omega Ik. And or maybe I should call this mu. And if you define lambda to be the convolution inverse of mu that always exists, then what you get is the Wick product map I described earlier in a multivariate case. So this is a simple observation, but in a certain sense a deep one, because when you adopt this approach, you can account for all Wick calculus in a universal way and simple terms. That's all in many situations. Anyway, what I would like to do now is to move to the non-commutative case. Non-commutativity here means that we're going to start from an associative algebra and what is called a state, which is a linear unital form on A. And we would like to understand how to define a theory of weak products in this framework. So following this pattern, it's going to be easy, but still one has to organize the reasoning in a systematic way. So what is important in the commutative case is the notion of cumulants. It's clear from the definition I gave of the exponential generating series of weak powers. The key in a certain sense is the notion of cumulant. In probability, but it's also true up to defining a proper notion of cumulants in quantum field theory. So here, the point is that from this point of view of cumulants, the situation is going to be more complex than in a commutative case because there are several variables of cumulants appearing naturally in non-commutative probability, which are called also sometimes quantum probability. In the classical case, for a family of random variables, omega 1, omega n, the associated cumulant is defined implicitly. So there are various definitions, but the simplest one is to define them implicitly by the following equation. So you look at the expectation of the product omega 1, omega n, and you want this to be the sum over all partitions of n of the product from E equals 1 to k, so over the blocks of the cumulant indexed by the cardinality of each block applied to what I will write omega pi, where omega pi is simply so let's say it that way. If S is a set S1 ST, omega S is going to be the sequence omega S1 omega ST. So this definition relies on the notion of partitions, and it extends to the non-commutative setting in various ways. So there are several notions of cumulants which are associated to notions of independence from the probabilistic point of view in non-commutative probability. And the first notion is the notion of tensor cumulants or tensor probability, which is obtained by the same definition as in the classical case. The only difference being that now we have non-commutative monomials appearing in the definition. And there are several families which are, in a certain sense, the only possible one from an algebraic point of view, for some universal properties reasons. And these three notions are the notion of free cumulants, which are associated to the notion of non-crossing partition. So instead of summing over all partitions, the definition of cumulants, you sum only over non-crossing partitions, which means that you look only at partitions that have this form. So this is non-crossing one, and you don't want partition like this, which is crossing. There's the notion of Boolean cumulants, which is associated to interval partitions of the integers. So interval partition means that you, in blocks, you allow only successive successive integers. And there's a last notion, which is the notion of monotone cumulants, which is associated to what are called monotone partitions. And monotone partitions are simply non-crossing partitions, but where one puts an order on the blocks in such a way that, for example, if you have a partition like this, you will order the blocks like 1, 2, 3. You want them, you want the hierarchical structure of blocks to be compatible with the ordering you put. So this defines 4 natural notions, and the only one from a certain point of view, universal point of view. 3 notions of cumulants, and this is going to be the starting point for theory of Wick non-commutative Wick polynomials. So I won't explain the classical case in so the non-commutative analog of the classical case, which is the one of tensor cumulants, because it's essentially accounted for by exactly the same strategy than in the classical case, except that one replaced the algebra of polynomials by the algebra of non-commutative polynomials. And if you do this, you obtain immediately a consistent theory of tensor Wick polynomials that also in the non-commutative framework, which formulas that are of course a bit different than the classical ones, because you have to take into account the ordering of elements in products. I will insist more on the 3 other notions of cumulants. And the important point is that from this, say, group theoretical or of algebraic approach to Wick polynomials, one has to start with a suitable of algebra structure. So here, the main object is going to be the tensor algebra over the tensor algebra, so the double tensor algebra over A, plus means that we remove the constants when going to the double tensor structure. Elements will be written in that way, so tensors, normal tensors are words, non-empty words, and we write sequences of words, so phrases in a certain sense, using the bar notation. So this belongs to tk of t plus of a. And there's a Hopf algebra structure on this object, which is defined in the following way. It's very close to the classical notion of unshuffled coproduct, up to a slight subtlety. If you have, so I will describe the coproduct on t plus of a. Okay. So on t plus of a, the idea is that if you have a word a1, an, you're going to send it to the sum over all subsets of n of as with the previous convention. So as means that we take the product over all ai's where I belongs to s. Tensor, what I write, ag1s, tensor agks, where these elements are the connected blocks in n minus s in the combinatorial sense. So connected means that you look at blocks that contains, so maximal block that contains successive integers in n minus s. If you do so, you obtain a coproduct. This coproduct splits actually into 2 pieces. As always, when you have this kind of shuffle or unshuffled structure. So here, this corresponds to the case where 1 belongs to S, and this corresponds to the case where 1 does not belong to S. I introduce this for reasons that will be clear later on. So this coproduct makes the double tensor algebra. So if you extend it multiplicatively to the double tensor algebra, it defines a Hopf algebra structure, and so we can mimic the construction, the classical construction of Wick products, axiomatized using the point of view of Hopf algebras, and define non-commutative Wick polynomials simply by taking the convolution of the identity with an element that I will write capital psi. So we take as in the probabilistic case the convolution inverse of a certain element that is going to be defined starting from this linear form phi. Psi is going to be defined by requiring multiplicativity, so psi omega 1 psi omega k if we have a double tensor, and on a simple tensor psi of say a1 an, which is a tensor of order n, is going to be defined simply by evaluating the linear form phi on the product in A of the AIs. Well, one has to distinguish between the word notation and the products in the elements of A. If you do this, what you get is what's called a character. It's an algebra map from this Hopf algebra Tt of A to the scalars. So it's a character which is invertible because it's unital, and it's invertible for the convolution, or either for general Hopf algebraic reasons, either simply by taking into account the fact that it's a unital linear form, and so this definition makes sense and defines a proper notion of non-commutative Wick polynomials. So starting from this, you can develop in the non-commutative setting the theory of Wick products from scratch. In particular, you can try to develop the order combinatorial theory. So looking at the formulas you can obtain that are going to involve partitions of the integers. I haven't much time left, so I will only explain one side of this theory. That was I should mention the name of Michael Ancelevich here. So what a series of papers on Apple polynomials. I think the title are Apple polynomials and their relatives. I'm not 100% sure of the title. So a series of 3 papers, where I started to develop the idea of non-commutative Wick polynomials from the point of view of polynomial sequences. So Apple polynomial sequences, which are the kind of families of polynomials that appear in the probabilistic setting. And so he developed the theory from this combinatorial approach. So families of polynomials satisfying certain combinatorial recursive identities. Whereas what we have tried to do is a completely different approach that leads to more structure in a certain sense. It's much more structural. We have all these Hopf algebra structures, and so group theoretical considerations that enter the picture, and it also allows to complete the combinatorial theory with these insights, and maybe a more systematic approach also. But strangely enough, it seems, at my best knowledge, that there's not much more on this. Although it's a very, I wanted overall to try to convince you that it's a very natural question. So starting from really the basics of classical quantum field theory and classical probability, what happens if you want to go non-commutative? In a certain sense, the first thing you have to consider, because it's really at the very beginning of the two theories, is the notion of a Wick product, non-commutative Wick product. And strangely enough, it seems that it was not developed much, except for this series of papers by Michael Ancelevich previously. So I will conclude on the link between non-commutative Wick products and cumulants. So in the classical case, you remember that the cumulant center for this formula. When x is a random variable. So the point is that there are similar formulas in the non-commutative case, but one has to be slightly more careful. So I will take only one example, the example of free probability. In that case, I explained that there's a well-defined notion of what are called free cumulants that come from non-crossing partitions. The point is that you can account for this construction in off-algebraic terms using these two products on the dual of the double tensor algebra. So the two products that are dual to what I wrote delta f and delta sup. If you use these products, you can define an exponential map for linear forms on the double tensor algebra by requiring this to be 1 plus, so 1 is the projection to the scalars, plus lambda plus lambda f lambda plus lambda f lambda f lambda and so on. So this is essentially what is called in physics or yes, also often in analysis the time ordered product for or the time ordered exponential, more precisely for operators.
Is it the dual law?
Yes, this is the dual.
Okay.
This is the dual product of the coproduct. Yes, exactly. This is the dual notion. So if you take this notion of exponential and you solve this equation, you can show that that kappa acting on t plus of a is exactly the free cumulant map that we did define using a combinatorial recursion. So if you do so, and it's also true that, so there's a dual notion of exponential. So there are several notions of exponential in this setting, and it's also possible to show that if you invert phi for the convolution, what you get is this other exponential applied to minus kappa. So from this, you see that and I will stop here. You see that the formula for the non-commutative Wick map can be rewritten as the convolution product of the identity with this anti-time order, in a certain sense, exponential of the linear form associated to cumulants, which is really the analog of the non-commutative analog of this classical formula. So starting from this, you can get plenty of cross formula for example, for the non-commutative Wick product, for the way you can expand the Wick product map in terms of free cumulants or the other notion of cumulants, Booleans or monotone cumulants. You can so you can also use this idea of structural transportation along W to create new off-algebra structures on the double tensor algebra that should make sense for this program of accounting of what happens when you move from commutative quantum field theory, in that sense, in the sense I explained, or commutative probability to non-commutative probability, or non-commutative quantum field theory, whatever is meant by this exactly. So, so I will stop here. The main point was really to explain the general strategy and why it should make sense, why this sort of algebraic combinatorial approach to these questions is natural, makes sense, and can be developed automatically if you adopt the right point of view. And in all approach, the right point of view is the Hopf algebraic one, because the structure, the Hopf algebra structure encodes all the combinatorial properties and the structural properties of Wick products. So I will stop here.
Do you have a question from the speaker? Yes, please, Emma.
Oh, maybe. Oh, okay. For non-commutative symmetric functions, we had to introduce. I wanted to ask you about the relation between this and the Heisenberg-wide algebra, which is done as you did, but with no commutation. You have two alphabets, and you have only AP, AQ plus minus Q. And we had a Fock space. Do you have here a Fock space like that? You know, you pile creations to a vacuum vector, and this is a faithful representation.
Yes, the Fock space. So representation of quantum field theory, it's closely related to the fact that you can move from so quantum field theory to probability, because if you, for example, if you take as a Fock space L2 functions on the real line, then you can use this to move from so physics to probability. This is probably the standard way of doing this, of establishing this sort of dictionary. Now, what is true is that usually people doing non-commutative probability, they tend to have two approaches. One probabilistic one, and the other one, so the quantum probability approach, is going to be to translate everything in the framework of Fock spaces, which is probably what you have in mind. And so this also appears in this framework. So, for example, free probability, you can associate a Fock space point of view. You just have to replace the classical rules for creation and annihilation operators by suitable ones. So, for example, one idea can be to, if you have a sequence of operators, since they are not commuting, you have to decide all creation, or so more precisely, all the annihilation operators are going to act on products of operators. And one way in the non-commutative setting to do this is to apply it on the first operator of a product and the last operator of the product, not by performing destructions inside products. So there are strategies like this to account of these constructions from the Fock space point of view. Okay. And actually, it's considered as important by people doing non-commutative probability, because they have they want to feature the link with
but here you
quantum physics.
For your Hopf algebra, you don't have a natural Fock space.
In a certain sense, the tensor algebra is already a sort of Fock space, and the double tensor algebra is a sort of double Fock space, whatever it means. But okay, I wouldn't go too much in that direction.
Very good.
Do you satisfied?
Yes.
Yeah.
Okay.
Oh, thank you very much, sir. You have another question? Quick, very quick question. Oh, no. So please.